File systems. File systems are essential for organizing digital data. They dictate how data is stored, accessed, and managed on different types of storage media, such as hard drives, SSDs, and memory cards. There are several prevalent file systems today, including NTFS, New Technology File System, mainly used by Windows operating systems. FAT, File Allocation Table, common in older Windows systems and on removable storage devices. HFS Plus, Hierarchical File System Plus, used in macOS environments. EXT, Extended File System, typically found in Linux distributions. Each file system has unique characteristics that affect how data is organized and retrieved. File system analysis involves examining the structures within a storage device. This process helps forensic experts to recover deleted files. Traces of deleted files often linger in the file system. Identify file attributes. Metadata provides important details, such as when a file was created or last accessed. Reconstruct file hierarchies. Understanding folder layouts can help piece together user actions. Reveal data fragmentation. Some file systems fragment data, necessitating reassembly for accurate analysis. Before any analysis can take place, it's essential to acquire and preserve digital media. This usually means creating a forensic image of the storage device to protect the data's integrity. A variety of forensic tools are available to assist in file system analysis, including Autopsy, an open-source tool with an easy-to-use interface for analyzing different file systems. The Sleuth Kit, TSK, a set of command-line tools designed for digital forensic analysis. InCase, a commercial software known for its extensive file system analysis features. Xways Forensics, a flexible forensic tool that excels in analyzing file systems. The file system consists of several important components. Experience analyzing and working with these structures is essential for effective analysis during the investigation. Previously in this book, we have explained the content of each item of the structure. Boot sector, the first sector of a storage device that holds vital information about the file system. File Allocation Table, FAT, a table that keeps track of data clusters on the storage media. Inodes, in Unix-based file systems, inodes contain metadata about files and directories. Master File Table, MFT, specific to NTFS, the MFT records attributes for files and directories. The recovery of the deleted files can still be done until the sector or data box gets overwritten in the disk or storage media. Specialized tools like Recuva or FTK Imager can assist in recovering deleted files during analysis. The timestamps on the data that can be provided by the file system metadata is of high importance because it contains the file creation time, the modification time, and access time. This is embedded in the metadata, along with additional information such as attributes, author, etc. The challenges that can be presented in the analysis of the file system is encryption. If the file or system is encrypted, it will create a great challenge to the forensic expert to gain access to the data and start the analysis. In the present time, encryption can be present depending on the system, but there are systems that have encryption since the initial configuration. Data fragmentation and system corruption can affect file integrity. When data fragmentation occurs, a file is stored in non-contiguous data blocks on the drive. If any of these blocks become damaged or corrupted, the file may become unreadable. Additionally, if a file is deleted and fragmentation is present, one or more of its sectors may be overwritten, resulting in incomplete or corrupted file recovery. MacFinder. Currently, macOS uses APFS, Apple File System, as its default file system, which replaced the legacy HFS Plus, Hierarchical File System Plus, back in 2017. HFS Plus is also known as macOS Extended. APFS was developed to enhance the performance of macOS by ensuring data integrity and providing storage efficiency for Apple devices. It operates on the concept of containers and volumes. Essentially, APFS organizes storage in containers, which are partitions or disk images that hold one or more volumes. These containers can span multiple physical devices or partitions, and each container can have multiple volumes that act as logical storage units. The operating system mounts and accesses these volumes as separate entities. One of the main features of APFS is its optimization for solid-state drives, SSDs, and other types of flash storage, which have become more prevalent in recent years. In contrast, the legacy HFS Plus was designed in the 1990s, when traditional hard drives were the dominant storage option, making it essential to adapt to the faster and more secure flash storage technology. A notable feature of APFS is its use of the copy-on-write technique, which writes data to new locations on the disk only when it changes. This helps reduce unnecessary disk operations and improves overall performance. APFS also supports snapshotting and cloning. The snapshot feature allows for system backups by creating read-only copies of the file system at specific moments in time. This means you can preserve the state of the file system, allowing you to revert to a previous state if something goes wrong. You can view these snapshots using the Disk Utility app by selecting Show APFS Snapshots in the sidebar, which helps save storage space by allowing multiple files to share the same base data until modifications are made. Another significant advantage of APFS is its native file-level encryption. This feature allows individual files to be encrypted with unique keys, adding an additional layer of security, especially in an era rife with hacking and cyber warfare. APFS is also integrated with Apple's File Vault technology, which enables full disk encryption. With File Vault, the entire contents of the disk are encrypted, safeguarding data, even if the physical device is compromised or stolen. Overall, APFS is designed to be a comprehensive and efficient file system that leverages modern technologies. In Finder, hidden files are often prefixed with .ds_store, which stores metadata about files and folders. On macOS, utilities like Terminal can be used to reveal hidden files. The following command enables the visibility of hidden files. Defaults write com.apple.finder. Apple show all files true. After running this command, restart Finder for the changes to take effect. The location of the files of each application in macOS can be located in the library folder in the disk. The databases are stored there, and either you open the application to find the location or navigate to the library folder in the root of the disk to get to the library folder. Look by the name of the application and the database location will be there. Alternate data streams. An alternate data stream, ADS, is a component of the Microsoft NTFS file system structure, introduced with the release of Windows NT. Originally, alternate data streams were intended to accommodate Mac files. Windows NT was designed as a server-centric operating system that allowed users to log in and access their own drives, as well as network drives. Microsoft recognized that many companies also utilized Macintosh computers and needed the capability to store Mac files on the server. Since Mac files are classified into two parts, a data part and a resource part, containing additional information, Windows are needed to maintain compatibility with this file system. However, these extra data streams are generally hidden from most Windows applications. An alternate data stream can contain any type of file that a standard host data stream can hold, such as text, images, videos, or even malicious code. Additionally, files can be stored within folders. Though a folder typically appears as an icon, leading to another directory, it is actually a file within the NTFS data structure. The default data stream includes metadata, indicating that the item is a folder at this particular directory location, allowing data to also be stored in its alternate data stream. This capability can be exploited for denial-of-service attacks, as a fully occupied hard drive cannot store additional data and may start to perform poorly, especially when it is large. Notably, there's no limit to how much data can be stored in an alternate data stream, so it is theoretically possible to completely fill a hard drive using this method. File analyzers. File analyzers are applications created to help to review files and data. There are some tools that can provide metadata information and are part of forensic software tools like FTK Imager or Autopsy. They can be presented as a solution for file analyzers. FTK Imager can provide information from the file. It will provide the location, name, timestamp, type of data, size. It will verify the hash information and additional metadata that can be located within the software. Autopsy forensics can create a full case for review of the extracted information. It can be as simple as a folder with files or a full physical image. Autopsy will analyze the metadata on the image and will create sections to provide a better analysis on the acquired data. It can create subcategories to review the different topics of each part of the image. Physical image creation. To create a physical image of a Windows-based computer, there are some items to be considered before starting the imaging process. There are different methods of acquiring the image of a hard drive. Live image. The process is to perform a forensic image while the computer is logged into Windows and uses the user's computer resources to create the forensic image. The process will create an E01 file export, split in 2 GB files, to an external device. This will capture volatile data and timestamps. The process is using FTK Imager and an external storage media. Admin permissions should be granted to the profile of the user that is logged to open FTK Imager. The process to create a physical image is the following. Open FTK image on the system that will be imaged. Click the Add button and select Physical Drive. Select the correct drive to image. Physical Drive 0 is the main drive, but identify the correct drive with the size and drive information. Then click Finish. The content of the drive will show in the evidence tree. To see the file list, select a folder or partition, and it will show the information that contains that partition of the directory. Right-click on the Physical Drive 0 or Selected Drive and click the Export Disk Image option. The Create Image Wizard windows will appear, and there is important information on this screen. There is the confirmation of the image source, the image's destination location, and the image process's characteristics that are verification and pre-calculation of the process. To start the wizard, click Add, select E01, click Next, and the Evidence Item Information screen will request information. Case number. Assign the case a case ID. It can be the name of the company, location where it is taken, or case number. Evidence number. Assign a number with a naming convention, like date case identification plus evidence consecutive number. Example, case 0, 01, underscore 2, 0, 2, 4, 0, 1, 5 underscore 0, 0, 1. Unique description. Add information about the system, make, model serial number, and the custodian name. Examiner. Name of the forensic analyst. Note. Provide any details of the device. Encryption key if the device is damaged, if it has any additional devices connected, etc. Select image destination. Select the destination path. Create a folder on the destination media with the evidence ID, and the image file should be the evidence ID. It is recommended to use between 1,500 to 2,000 megabytes for image fragment size. The standard in compression should remain the same 6. Click Finish. The destination location should now be added, and it is time to review the information on the Create Image window. Once everything is confirmed, click Start. The imaging process will start. The Creating Image window will provide information of the process, and once the image is complete, it will show the evidence summary. The verification process will take the same time as the imaging process. Once the image is complete, the destination path will contain the full set of files that will create the image when processing is needed. This image cannot be altered. It can be mounted but read only. There will also be an image summary file with the log information of the image. The image verification process is always required to make a comparison of the hash values of the image at the end of the verification in the evidence summary. It will contain the verification hash that will confirm that the image is a valid image and the data has been verified. Assembling images and using automated tools. To assemble the images taken from Windows devices, such as FTK Imager, Imager, or any forensic software, there are specialized tools that can help us to translate the image that was acquired with the forensic software into a more common and comprehensive information. Tools like Encase Forensics, Autopsy Forensics, Axiom Process, etc. are some of them. The user of Autopsy is a free tool that is reliable with the use of forensic images. It is required to have a computer that is powerful enough to process the data. RAM memory will be of use when processing data, but also processing power is needed. To assemble an image using Autopsy Forensics, follow the next steps. Create a new case in the Welcome window. Assign a case name and the base directory for the case to be saved. Fill out the option information if it's present. This will help to identify the case when it is open. Click Finish, and Autopsy will start to create the databases needed for this investigation. Autopsy will ask you to add data sources. Select Generate New Hostname based on data source name. Select Disk Image or VM File on the Select Data Source Type window. Select the path where the E01 image is located and select the file. Click Open and click Next. The Configure Ingest window requires specifying the data to be analyzed from the image. If the goal is to detect encryption, examine recent activity, identify file types, or perform picture analysis, the appropriate options can be selected. Once configured, Autopsy will begin processing the data. After the image has been created in the Autopsy environment, we can start with our investigation. There are categories on the left side of the screen that will help us to understand the different aspects of the investigation, such as connected devices, installed programs, operating system information, recent documents, recycle bin, programs that have been executed, USB devices attached, web history, web searches, encryption status, etc. The main screen of Autopsy will give us a large set of actions that we can perform. We can analyze images or videos, communications, geolocation, timeline, etc. We can add more data sources. One key element of all the tools is the resources that the computer running the investigation will require. Log extraction and analysis. Logs are crucial records that detail system and application activities, making them indispensable for forensic investigations, incident response, and monitoring system health. By analyzing these logs, analysts can uncover suspicious activities, track unauthorized access, and gain insights into overall system performance. Windows event logs are integrated logging systems that record various types of system events, including those related to security, applications, and the operating system itself. The primary types of logs include application logs, events generated by applications running on the system; system logs, events logged by Windows system components; security logs, records of security-related events, such as login attempts and resource access; tools for extraction and analysis; event viewer, functionality, a graphical interface that allows users to view and manage event logs on Windows systems. Users can filter logs based on date, event severity, for example, error warning information, and source. Analysis. Investigators can search for specific events or patterns, like failed login attempts or application errors, which may indicate security issues. PowerShell. Extraction. PowerShell provides CMDlets like getEventLog and getWinEvent for programmatic log extraction. These commands are particularly useful for automating processes and handling large data sets efficiently. Example command: PowerShell, copy code, getWinEvent, logname security, where object, id eq4625 tar. This command retrieves failed login attempts, event ID 4625, from the security log. Log parsing. Tools. Utilities like Log Parser can analyze Windows logs in various formats, enabling custom queries and reporting. Scripting. Analysts can develop scripts to automate the log extraction and analysis process, focusing on specific events or anomalies. Common indicators of intrusion. Failed logins. A spike in failed login attempts may suggest brute force attacks. Unusual logon hours. Logins occurring outside normal business hours can raise suspicions. New user accounts. Unexpected accounts or escalated privileges can indicate unauthorized access. Third-party logs. Third-party security tools generate their own logs, adding context to incidents. These tools may include antivirus programs, firewalls, intrusion detection systems, IDS, and security information and event management (CEM) solutions. Examples of third-party logs. Firewall logs document traffic that is either permitted or blocked by the firewall, helping to identify unauthorized access attempts or unusual traffic patterns. Intrusion detection system (IDS) logs capture alerts and events linked to potential intrusions, providing insights into attack vectors. Antivirus logs record detected threats, actions taken against them, and scanning activities, which can assist in identifying malware infections. Management, generation, and analysis of shadow copy. Shadow copy is a Windows service that allows the operating system to back up open files and restore files to a certain extent. First introduced in Windows XP, shadow copies function by creating a snapshot of the drive. The primary goal of this feature was to enable backup software, such as NT Backup, to back up open files. In the initial release, shadow copy could only create a temporary snapshot for later backups. Subsequent versions of Windows allow users to restore files from these snapshots. However, it's essential to note that shadow copies should not replace regular backups. This is because snapshots only record changes. If a file hasn't changed, it won't be included in the snapshot. If a user later deletes a file not stored in the shadow copy, the only way to recover it is from a backup. Additionally, shadow copy is limited by the allocated storage space and the number of snapshots that can be created. Once the storage area is full, the oldest snapshot will be deleted to make room for new ones. When shadow copy is enabled, it allocates a storage area, which the administrator can choose, but it must be greater than 300 megabytes. When a shadow copy runs, it stores files that have been modified. For instance, if certain files on the drive change and a shadow copy service runs next, these modified files are copied to the shadow copy data store. If another file changes after the first shadow copy runs, nothing will change in the storage area until the shadow copy runs again. During the next run, the modified file will be copied to the storage area. This process repeats each time changes occur. The storage area effectively holds changes rather than complete files, which allows it to manage frequent changes to the same files efficiently. Eventually, the storage area may become full, at which point the oldest shadow copy will be removed. Furthermore, shadow copy can only store 64 changes to a file. Once this limit is reached, the oldest version will be removed to make space for new changes. In summary, while shadow copy is a useful feature for file restoration, they should not be seen as a replacement for regular backups. Administrators do not have control over which files are removed from the shadow copy storage area. Therefore, if you want to ensure that a file remains available, it's crucial to back it up in a separate location. Watch the following video, How to Enable Previous Versions and Shadow Copy on Windows Server by Danny Moran.